This video is prepared by Aavya classes. Please subscribe the channel, raise your doubt and watch the video for sure success in JEE, AIIMS and NEET. Now we will see the problem based on the concept we have learned. And first problem is a convex lens of refractive index 3 by 2 has a power of 2.5 diopter in air. If it is placed in a liquid of refractive index 2, then we have to find the focal length of lens now. So basically we have to apply the lens maker's formula, and it is given here that P is equal to 5 by 2 diopter. So it is equal to 1 by F as lens is placed in air. So now if you apply the lens maker's formula, then 1 by F is equal to mu minus 1 into 1 by R1 minus 1 by R2, and the value is equal to 5 by 2 is equal to mu minus 1 into 1 by R1 minus 1 by R2. Mu is equal to 3 by 2. So 3 by 2 minus 1 is 1 by 2 into 1 by R1 minus 1 by R2, and from there we get 1 by R1 minus 1 by R2 is equal to 5. So this is our equation 1. Now if we place this lens in a medium having refractive index 2, then just calculate the focal length of lens by using lens maker's formula. So if new focal length is f1, then 1 by f1 is equal to mu lens divided by mu medium minus 1 into 1 by r1 minus 1 by r2. So it's equal to mu l is 3 by 2. So 3 by 2 divided by 2, the refractive index of medium is 2, 1 by R1 minus 1 by R2. So it's equal to minus 1 by 4, 1 by R1 minus 1 by R2. And from equation 1 and 2, we get 1 by F1 is equal to minus 1 by 4 into 5, that is minus 5 by 4. So F1 is equal to minus 4 by 5. So in meter, so if we change it to centimeter, so 4 into 100 by 5, that is minus 80 centimeter. So the new focal length of lens is minus 80 centimeter. Now if you change here, the earlier it was the convex lens having the focal length comes with positive sign, so it was a converging lens. Now the focal length changes to a negative value, that is the lens becomes a diverging lens. So we have already learned this concept that if the refractive index of medium is more than the refractive index of lens, then the lens changes its behavior. It will, and then opposite behavior is observed, that is a convex lens behave as a divergent lens, and a divergent lens behaves as a convergent lens. This is also a very good problem. Diameter of a plano-convex lens is 6 cm and thickness at the center is 3 mm. The speed of light in material of lens is 2 into 10 to the power 8 meter per second. The focal length of lens is. You have given 4 options and you have to pick the correct one. Now first we will draw the figure pertaining to this problem. And suppose this is our plano-convex lens. This is our plano-convex lens. So this is a part of a sphere having radius equal to r. So this curve, this convex surface, that surface 2, is a part of a sphere having radius equal to r. So this is having radius equal to r. Consider this point as O and this point as A, this point as B. Then the problem says that the diameter of plano-convex lens is 6 cm. So this diameter AB is equal to 6 cm. So AB is equal to 6 divided by 2. That is, as per the problem, BC is equal to 6 cm, diameter of the plano-convex lens. So AB is equal to AC is equal to 3 cm. Now, if you see that thickness at the center is 3 mm, so this is 3 mm. Now, as per the Pythagoras theorem, that OA square plus AB square is equal to R square, and the value of OA is R minus 3 mm. So we write 3 mm as 0.3 centimeter. So R minus 0.3 square plus AB is equal to 3 centimeters, so 3 square, and we have to calculate the value of R, so R square. From there, if we solve it, R square plus 0.09 minus 0.6 R plus 9 is equal to R square. So from there we get 0.6 R is equal to 9.09, and R is equal to 9.09 divided by 0.6, that is approximately equal to 15. So why we calculated the radius? Because you have to calculate the focal length, and in order to calculate the focal length, the formula is 1 by f is equal to mu minus 1 by r1 minus 1 by r2. So the radius of curvature for this plane surface is infinity. However, the radius of curvature of this convex surface is unknown. So you will first have to calculate this radius of curvature. Second, you have to calculate the refractive index. So how you will calculate the refractive index? The speed of light in material is given. From there you can calculate the refractive index. So refractive index of material, mu is equal to velocity of light in vacuum divided by velocity of light in that medium. So velocity of light in vacuum is equal to 3 into 10 to the power 8, and velocity of light in that medium is 2 into 10 to the power 8. So from there we get mu is equal to 3 by 2. And R comes equal to 15. So now we can apply the formula very easily, that 1 by F is equal to 3 by 2 minus 1, and this is R1, this is the first surface R1, this is R2. So the radius of first surface is infinity, so 1 by infinity minus, and radius of second surface comes with a negative sign, so minus 15. As if light ray if the object is placed here, then light ray comes in this way. So it's 1 by 2 minus 0 minus plus 1 by 15. So it's 1 by 2 into 1 by 15, that is equal to 1 by 30. So F comes equal to 30 centimeter. So the focal length of this plano-convex lens is 30 centimeter. So now we will move to next problem. And this problem I have picked from AIIMS 2007. When a convex lens of focal length f is dipped in water, its focal length becomes 4f by 3. The reason the focal length of convex lens in water becomes 4f. So we are talking about convex lens, and the formula of focal length for convex lens is 1 by f equal to mu minus 1 by r1 minus 1 by r2. This is our lens maker's formula, and we have to apply this formula. So in first case, when it is in air, then 1 by fa is equal to 3 by 2 minus 1 by r1 minus 1 by r2. And when it is dipped in water, then it's f1 by fw. 1 by fw, the refractive index of water is not given. We may assume it 4 by 3. So 3 by 2 divided by 4 by 3 minus 1 into 1 by r1 minus 1 by r2. As we know that here the mu is equal to mu lens divided by mu medium. So 1 by fw is equal to 9 by 8 minus 1 by r1 minus 1 by r2, that is 1 by 8 into 1 by r1 minus 1 by r2. So clearly if this is our equation 1, this is our equation 2, then 1 divided by 2 is equal to fw by fa is equal to 1 by 2 1 by r1 minus 1 by r2 divided by 1 by 8 1 by r1 minus 1 by r2, and from there we get it's equal to 8 by 2, that is 4. So fw is equal to 4 fa. Anyway, we have learned this concept so many times, so clearly the focal length of convex lens in water becomes 4 times the focal length of same lens in air. So reason is correct, assertion is false. Now the next problem is from JEE Mains 2014. A thin convex lens made from crown glass mu is equal to 3 by 2 has focal length f. When it is measured in two different liquids having refractive indices 4 by 3 and 5 by 3, its focal length become f1 and f2 respectively. The correct relation between the focal lengths is, and you have given four options, you have to find the correct one. Again, we will apply the lens maker's formula. So if I apply the lens maker's formula, then first consider the refractive index of that glass in air. So 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2, as it is a thin convex lens. So we may draw the figure also for more clarity. R1 comes with positive sign and R2 comes with negative sign. Anyway, it is immaterial to consider the sign here. So 1 by F is equal to 3 by 2 minus 1 into 1 by R1 minus 1 by R2. It is 1 by 2 1 by r1 minus 1 by r2. So this is our equation 1. Now we consider that the same lens is placed in a medium having refractive index 4 by 3, then its focal length become f1. So 1 by f1 is equal to 3 by 2 divided by 4 by 3 minus 1, 1 by r1 minus 1 by r2, and it is equal to 9 by 8 minus 1, 1 by r1 minus 1 by r2. So it's 1 by 8, 1 by r1 minus 1 by r2, and it is equal to 1 by 4f. So 1 by f1 is equal to 1 by 4f, and f1 is equal to 4f. So this is our equation 2. Now, if we see that if the lens is placed in a medium having refractive index 5 by 3, then the focal length becomes f2. So 1 by f2 is equal to 3 by 2 divided by 5 by 3 minus 1, 1 by r1 minus 1 by r2, and is equal to 9 by 10 minus 1 into 1 by r1 minus 1 by r2. So it is minus 1 by 10, and from there we get it's minus 1 by 5 f. So f2 is equal to minus 5 f, and f1 is equal to 4f. So if you see that f1 is greater than f1 is greater than f, it's correct, and f2 becomes negative. So if you see the option, then option 2 is correct. Now the next problem is problem number 5. Lens is made of flint glass having refractive index 1.5. When the lens is immersed in a liquid of refractive index 1.25, then the focal length is. So it's the refractive index of material of lens is given, refractive index of medium is given, and you just have to make a calculation by applying the lens maker's formula. So it's very easy, that 1 by f is equal to 3 by 2 minus 1, 1 by r1 minus r2 when the lens is placed in air, and when it is immersed in liquid, then if immersed in liquid, then 1 by f1 is equal to 3 by 2 divided by 1.25, that is 5 by 4 minus 1, 1 by r1 minus 1 by r2, that is equal to 12 by 10 minus 1, 1 by r1 minus 1 by r2, that is equal to 1 by 5, 1 by r1 minus r2. Now if we divide this equation 1 and 2, then we get the ratio, and dividing it we get f1 by f is equal to 5 by 2, that is equal to 2.5. So f1 is equal to 2.5 f. So clearly the focal length of focal length of a lens changes or increases by a factor of 2.5. Now we'll move to next problem, and this is also very good problem. In fact, we will learn more concept about power in this problem. A thin glass having refractive index 1.5 has an optical power of minus 5 d in air. Its optical power in liquid medium having refractive index 1.6 is. So it is given that P is equal to minus 5d in air. So as we know that P is equal to 1 by F, and it is equal to minus 5 is equal to mu minus 1 into 1 by R1 minus 1 by R2. So its mu is equal to 1.5. It is 3 by 2 minus 1 into 1 by R1 minus 1 by R2. So we get 1 by 2 into 1 by R1 minus 1 by R2. Our first equation is minus 5 equal to 1 by 2 1 by R1 minus 1 by R2. This is our first equation. The second equation is that if we consider the focal length of a lens in that medium is f2, then 1 by f2 is equal to 1.5 mu lens divided by mu medium, that is 1.5 divided by 1.6 minus 1 into 1 by R1 minus 1 by R2, that is equal to 15 by 16 minus 1, that is 1 by 16 with a minus sign, 1 by R1 minus 1 by R2. Now if you divide it, then you get it 5f2 with a negative sign, that is minus 5f2 is equal to 1 by 2 divided by 1 by 16 with a minus sign. So we get 16 by 2, that is 8, in fact minus 8. So f2 is equal to minus 8 by 5 and minus sign. So f2 is equal to 8 by 5. Then clearly f2 is equal to 8 by 5. So 1 by f2 is equal to 5 by 8. And the refract and the power of this lens in a medium having refractive index. So we have to calculate the power of lens. So power of lens in liquid medium. So power of lens in liquid medium is equal to, it is P is equal to mu medium divided by F medium. So mu medium is equal to 1.6 and the focal length of that medium is equal to 8 by 5. So from there if you solve it, then we get it's a 1 diopter. So if you see here that here also the refractive index of material is more than the refractive index of glass lens, and because of this the divergent lens becomes a convergent lens. Now what is this concept, power of lens in a different medium? So for this we just learn the concept of power for a while, and then we will understand that how we calculate the power in different scenarios. So the power of a lens in air is given by 1 by F. So power of lens in air is equal to 1 by F. The power basically defines that what is the converging or diverging power of a lens. So if a parallel beam of light comes and hit the principal axis at a point F, and if F is closer to the optical center, then we say that it has more power. So basically power is inversely proportional to F. Like if you consider this convex lens, and if light ray strikes at this point, we have already discussed this in case of thick versus thin lens, that if this is the focal point, then power is equal to 1 by F. If we consider this lens as a thick lens, then it will converge light ray more close to this optical center, and its focal length will decrease, the power correspondingly increases. So we have learned these concepts. Now what is basically power? So for this we just first learn the concept of surface power. So consider this is a refracting surface having one side its refract one side the refractive index is mu2, and this side the refractive index is mu1. The radius of this surface is a spherical surface is r1. Then the surface power is defined as P1 is equal to mu2 minus mu1 divided by r1. That is, the lens surface power can be found by using its index of refraction and the radius of curvature. So lens surface power can be found by refractive index and radius of curvature. So for this surface, the value is mu2 minus mu1 by r1 is the surface power. Now if you consider the second surface, if you consider this surface as mu2, this surface as mu3, then the power is equal to P2 is equal to, and this radius of curvature is R2. Then here if you consider R1 is equal to, so P2 is equal to mu3 minus mu2 by r2. Now then we have to apply the sign convention. So we consider the direction of incident light ray as positive. So if light ray goes in this way, then this direction is taken as positive, this direction will be negative, and here also this direction will be taken as positive and this direction will be taken as negative. So if we apply the sign convention, then power P1 is equal to mu2 minus mu1 by plus R1, and P2 is equal to mu3 minus mu2 divided by minus R2. Now if we add these two surfaces, then we get a convex lens. So we are adding these two surfaces having the refractive index of medium is mu1 and mu3 respectively, and the refractive index of lens is mu2. Then the power is the combination of these two surfaces, and we have to add this P1 and P2 to get the net power. So total power P is equal to, we call it P total. So P total is equal to P1 plus P2, and it is equal to mu2 minus mu1 divided by R1 minus plus mu3 minus mu2 divided by minus R2. So from there we get mu2 minus mu1 by R1 plus mu2 minus mu3 by R2. So this is our total power for this system. Now if you consider mu1 is equal to mu3, like if I consider mu1 is equal to mu3, then we get power is equal to mu2 minus mu1 into 1 by r1 plus 1 by r2. So basically, so in this way we get power P is equal to mu2 minus mu1 into 1 by r1 plus 1 by r2. So if we divide this term by mu1 and multiply it by mu1, then mu1 into mu2 by mu1 minus 1 1 by r1 plus 1 by r2. So if it is a convex lens having the refractive index mu2 and placed in a medium having refractive index mu1, then the power is given by mu1 by fw, where fw is, in fact it's a medium, so we just write f medium. So where 1 by f medium is equal to mu lens divided by mu medium minus 1 into 1 by r1 plus 1 by r2, and that is equal to mu 2 by mu 1 minus 1 into 1 by r1 plus 1 by r2. So clearly we may see that the power in this case is equal to refractive index of that medium divided by the focal length of lens in that medium. So we learned this concept that if we place a lens, suppose this is the lens, and if we place this lens in a medium having refractive index mu medium or mu m, and the refractive index of this lens is mu l, then power p is equal to mu m divided by fl or fm, where fm is the focal length of lens in the medium. We have also learned the concept of surface power, and if we add the surface power of two surfaces, then we get the surface power of a lens. So based on that concept, we will calculate the power in different kind of situations. So first situation is that the power of a convergent lens having different refractive index on both sides, so mu1, mu3 and mu2. The radius of curvature is r1 and r2. Then we get the value of power is equal to p1 plus p2, and p1 is equal to mu2 minus mu1 divided by r1 plus, and p2 is mu3 minus mu2 divided by minus r2. So mu2 minus mu1 divided by r1 plus mu2 minus mu3 divided by r2. This is the power in this scenario. Now we consider the case that when this lens will become a convergent lens, when this lens will become a divergent lens. So this is also important concept. You will just note it down. Consider the case when r1 is equal to r2 is equal to r. Then if you calculate the value of power, then power p is equal to mu2 minus mu1 plus mu2 minus mu3 into 1 by r plus into 1 by r. So from there you get 1 by r into twice mu2 minus mu1 minus mu3, and you get 2 by r into mu2 minus mu1 plus mu3 divided by 2. So clearly when mu2 is greater than mu1 plus mu3 by 2, that is when mu2 is greater than mu1 plus mu 3 by 2, then power becomes positive and it will work as a convergent lens. So in that scenario it will work as convergent lens. We have already learned that concept. You can apply this concept in the runtime also. So it will work as a convergent lens, and similarly when mu2 is less than mu1 plus mu3 by 2, then it will work as a divergent lens. Now we will calculate the power in some situations. So consider this lens, and you have to calculate the power of this lens, like r1, r2, and both r1 and r2 is equal to r, and this is the medium having refractive index equal to mu2, this is mu1, this is mu3. Then power p is equal to p1 plus p2, and p1 is equal to mu2 minus mu1 divided by that is difference of refractive index at both surfaces divided by r1, and you have to consider the sign convention also. So considering the light ray is moving in this way, then this direction is considered as a positive. The direction of incident light ray is taken to be positive, and this is negative. So mu2 minus mu1 divided by minus r1 plus mu3 minus mu2 divided by minus r2. Sorry, it's a plus r2 because this direction is taken to be positive. So it's mu2 minus mu1 divided by minus r plus mu3 minus mu2 divided by r. So based on this condition, if it comes with a negative sign, then it will work as a divergent lens. If it comes with a positive sign, then this lens will change to a convergent lens. So we can calculate all kinds of power. We can calculate the power of all kinds of lens based on this concept. Like if this is the mu2, mu1, mu3, and this radius is r1, this radius is r2. So we just calculate the value of power after considering the sign convention also. Then it's a mu2 minus mu1 divided by r1 plus mu3 minus mu2 divided by r2. So this will be the power in that scenario. Here r1 comes with a positive sign, r2 comes with a positive sign because we are taking this direction as a positive, and in the difference of refractive index at first surface is mu2 minus mu1, and at the second surface mu3 minus mu2. Again, if power comes with a positive sign, then it will be a convergent lens, otherwise it will be a divergent lens. And if power comes with and if power will be zero, then it will neither converge nor diverge the parallel beam of light rays. So this is all concepts about the power. If you get any doubt in this, then you just make comment in the comment section and I will happy to solve your doubt. So now we'll move to the next problem, and this problem is from IIT JEE 2010. This is very good problem. In fact, two transparent media of refractive indexes mu1 and mu3 have a solid lens shaped transparent material of refractive index mu2 between them as shown in figure in column 2. A ray traversing this media is also shown in the figure. In column 1, different relationship between mu1, mu2 and mu3 are given. Match them as the ray diagram is shown in column 2. So here in the column 1, the relation between refractive indexes are given, and column 2 ray diagram are shown. So you have to match them. And this is a very good problem. In this problem we will learn the concept of a ray diagram. So first is when mu1 is less than mu2. So first is when mu1 is less than mu2. Nothing has been said about mu3. So mu1 is rarer medium and mu2 is denser medium. So if a light ray moves from denser to, so I just redraw it here also. So if a light ray moves from a rarer to denser medium, then it moves towards the normal line. So suppose this is our normal line, and if a light ray moves in this way, then it will definitely move towards the normal line. Now if mu3 is less than mu2, then it will move away from the normal line, that is it will strike the principal axis. And if it is denser with respect to mu2, then it will move away. So the light ray from here may move in this way or it will move on that way. This is true for a rarer and this is true for a denser. So as mu3 is nothing, as nothing is said about mu3, so we consider both cases and we may say that the light ray may move in between of them. So here if you see that the light ray coming without any deviations, it means mu3 is equal to mu2, and the option P is correct for option A. So for option A, P is correct. Now consider the value Q. See here in the Q, the light ray is moving away from the normal line. So clearly it's a wrong because mu2 is a denser medium. So Q will not be correct. Now if you see the R, then I just draw the figure for this R also. In fact, I will just draw for the Q also. So for Q, this is the light ray and this is the light ray moves away from the normal line. However, this is our denser medium. So if I consider the figure R, then here this is our normal line and light ray comes in that way. So it must move towards the normal line. So it must move in that way. So clearly if you see the figure, then the light ray moves in that direction only. So R is also correct. R is also correct. Now we will see the S. So S, if you see, So I will draw the figure S also. Here the light, here this is the normal line, the light comes in that way. So after refraction it should move in towards the normal line, so it moves away from the normal line, so again it is incorrect, so S is incorrect. And similarly if you see that T is also incorrect as the light ray moves away from the normal line. So for A, P and R is correct. Now we see the case B. Case B is when mu1 is greater than mu2. So clearly now the light ray is coming from denser to rarer medium, and in this way it will move away from the normal line. So clearly figure A will not happen because here the light ray is moving towards the normal line. The Q is correct, S is correct and T is correct. I will show any figure. Consider the figure S. So this is our figure S. I will draw the figure T also. So this is our figure T. Light ray is moving in this way, and this is our image line. So light here, the refractive index of second medium is less, so it will move in this way. It will move away from the normal line, making some angle R greater than angle of incident I. So T is also correct, and similarly it's true with the S also, it's true with the Q also. So Q also it moves away from the normal line. So Q, S, T are correct. Now if you see the option C, then mu2 is equal to mu3. So when mu2 is equal to mu3, it means these two mediums having the same refractive index. So we will not observe any deviation at the second surface. So here P, we don't have any deviation at the second surface in figure P, in figure R and in figure T. So for options, so for C we have P, R, T are correct. Now if you see the option D, then mu2 is greater than mu3. So clearly mu2 is greater than mu3, that is the lens medium is a denser medium. So if lens medium is a denser medium, then it should move in figure A, it should move in that way, and here it's been, we observe no deviation, so clearly P is not correct. Here if you see the figure B, so here the light ray, as it is a dense, as it is a rarer medium, so it should move away from normal line, so it's true, and in this way Q is correct. Again if you see the option R, then option R, the image is this one. Now the normal line is this way, and the light ray should move away from the normal line, and here we observe no deviation, so it's wrong. Here also we observe no deviation, so it's wrong. So now we'll see the option C, option S. So in option S, as it's a rarer medium, so light ray moves away from the normal line, and it moves away from the normal line, so S is also correct. So if you see in this way, for A, P and R is correct. For B, Q, S and T are correct. For C, P, R and T are correct. And for D, Q and S are correct. Now we move to our next problem, and this problem is from AIIMS 2011 and is assertion region based. So assertion is when a white light is passes through a lens, violet light is more refracted from red light. Region focal length of red light is greater than violet light. Many of you already know this concept that when the white light ray passes through the lens, then violet light is more refracted than the red light, and both light are unable to focus at a single point, and we call it as chromatic aberration. So anyway, I will just explain it also. So if you consider the visible spectra, then it's a form of Vibgyor, and the order of increasing wavelength is this way. So lambda red is greater than lambda violet. So again we have one Cauchy relation which gives you an idea about the refractive index of material and the wavelength of light. So as we know that the wavelength of light and the relation between the refractive index is equal to mu is equal to a plus b lambda square. So if you don't know about it, then just refer my notes in the refraction through a medium. So there you will get this Cauchy equation and how it can be used. What are the limitations of Cauchy equation? So clearly lambda r is greater than lambda v, so mu r is less than mu v. Now the focal length of any material is directly proportional to mu minus 1. So clearly 1 by fr is less than 1 by fv, and focal length of violet light is less than the focal length of red light. So because of this, the focal length of red light is greater than the violet light is the correct reason, and because of this, when a white light is passed through a lens, then the violet light is more refracted than the red light. So I will show it from the ray diagram also. Consider this is the convex lens, and consider this white light ray is passing through this lens, and here suppose red light. So this is our FR. So red light focused at this point, while the violet light focused at this point. So we call it FV. And similarly, this can be observed in case of diverging lens. So this is our violet light, this is our red light. So in case of diverging lens, this is our red light, this is our violet light, this is our violet light, this is our red light, and as these are diverging light rays, so real image is not formed. So this is the focal length of from this optical center C. So this is the focal length of red light, this is the focal length of violet light. Now we'll see to next problem, and this is in fact a very good problem. A hollow double concave lens is made of very thin transparent material. It can be filled with air or either of two liquids L1 and L2 having refractive indices N1 and N2 respectively, where N2 is greater than N1 greater than 1. Lens will diverge a parallel beam of light if it is filled with, and you have given 4 options and you have to find the correct one. So first we will apply the lens maker formula and try to understand what will be the option. So lens maker formula says that 1 by f is equal to mu lens divided by mu medium minus 1 into 1 by r1 minus 1 by r2, and it's a hollow double concave lens. So basically it's a hollow double concave lens. Now it's a hollow, so inside we can fill any other material also. So it's a hollow. Now for a concave lens or for a diverging lens, if the lens will be able to diverge a parallel beam of light ray, then its focal length must be negative. So clearly mu, the 1 by f should be less than 0. 1 by f is composed of two parts, 1 by r1 minus 1 by r2 and mu l minus mu medium minus 1, and as it is a double concave lens, so radius this r1 turns out to be negative. The light ray goes in this way, so this direction is taken as positive, this direction will be negative, so r1 will be less than 0 and r2 will be greater than 0. So 1 by r1 minus 1 by r2 must be less than 0. So clearly this term is of negative value, so this term must be positive value in order to make 1 by f less than 0. So it means mu l by mu medium minus 1 must be greater than 0, and mu l must be greater than mu medium. So the refractive index of lens material must be greater than the refractive index of medium. Now based on this concept, we just explored all options. So first option is air and placed in air. So if air and placed in air, then the lens medium is air, medium is also of air. So this condition will not satisfy, this is not there. And if you see the option, then n2 must be greater than n1. So if we fill lens with n2 medium and medium having n1, then this hollow double concave lens will diverge the light ray. So this is our first option. And second option, if we make lens having a medium n1 and the medium is air, then also it will diverge the light ray. So for both conditions, the light ray will diverge. So if you see the option D is correct. Now we will move to our next problem. A meniscus lens is made of a material of refractive index mu2. Both its surfaces have radii of curvature r. It has two different media of refractive indices mu1 and mu3 respectively on two sides, is shown in the figure. Calculate its focal length for mu1 less than mu2 and mu2 less than mu3 when light is incident on it as shown. So here this is the direction of incident light ray, and if you draw the ray diagram, then as mu2 is greater than mu1, so it will move towards the normal line. And so if this is our principal axis, then it will hit the principal axis at this point, and we call it I1. So I1 is the image formation due to first surface, and it will serve as a virtual object for the second surface. For the second surface, if this is the radius of curvature, again having the same radius, so it is also in this way. And if this is the angle of incident, this is our angle of incident, then the angle of refraction will be less as the ray is moving from rarer to denser medium. So it will move again further in this way, and finally it will form a image equal to I. So this is our V, and this is our final image. So we will have to apply the refraction through the curved surface, and for the first surface we will first apply, and then we apply for the second surface. So for first surface, and our formula is mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. And if I put the value of V, then V is V1, so mu2 by V1 minus mu1 by infinity, U is infinity, and we get mu2 minus mu1 by R. R comes with a positive sign because the direction of incident light ray is taken as a positive. So mu2 by V1 is equal to mu2 minus mu1 by R. This is our equation 1. Now for second surface, its light ray is going from medium mu2 to medium mu3. So mu3 by V minus mu1 by V1. This V1 serves as the object for the second surface. It's a virtual object for the second surface, and it is equal to mu3 minus mu2. So mu3 minus mu2 divided by R. So from there we get, again it comes with a plus R. So mu3 by V minus mu2 by V1 is equal to mu2 minus mu1 by plus R is equal to mu3 minus mu2 divided by plus R. So from there we get mu3 by V is equal to mu3 minus mu2 plus mu 2 minus mu 1 divided by r, that is equal to mu 3 minus mu 1 by r. So from there we get v is equal to r mu 3 divided by mu 3 minus mu 1. So clearly the focal length for this situation is equal to r mu 3 divided by mu 3 minus mu 1, as the parallel beam of light ray is focused at the point having length equal to focal length. So now we will see next problem, and this is a bit easy problem. So a convexo-concave diverging lens is made of glass of refractive index 1.5 and focal length 24 cm. The radius of curvature of one surface is double that of the other. Then radii of curvature of two surfaces are. First thing is that it's convexo-concave lens. So it's convexo-concave diverging lens. So we just first draw the convexo-concave diverging lens. This is the convexo-concave diverging lens, and this is our concave surface. This is our convex surface. Concave surface is steeper than the convex surface. That is, the radii of curvature of a concave surface will be less. So if its radius is r and its radius is r, then its radius is 2r. So now, if we apply the lens maker's formula, then 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2. So mu is equal to 1.5. So we get 3 by 2 minus 1 by r1. If the light ray is coming in this direction, then this direction will be taken as positive, this direction will be taken as negative. So minus 1 by r minus 1 by 2r. So we get, and it's a diverging lens. So if it is diverging lens, then the focal length must come with a negative sign. So minus 1 by 24, and this is the important concept. You should know that if you see the diverging lens, then apply minus 1 by 24. If it were converging lens, then it would have been 1 plus 1 by 24. So minus 1 by 24 is equal to 1 by 2 into 1 by 2r minus 1 by r. That is 1 by 2 into minus 1 by 2r. So from there we get r is equal to 6 centimeter and 2r is equal to 12 centimeter. So the radii of curvature of two surfaces are 6 centimeter and 12 centimeter, and option A is correct. So this is the last problem of this section, that lenses are constructed by material of refractive index 1.5. The magnitudes of radii of curvature are 20 centimeter and 30 centimeter. Find the focal lengths of possible lenses with row specifications. So the radii of curvature are given as 20 centimeter and 30 centimeter. So R1 is 20 centimeter and R2 is equal to 30 centimeter, and mu is given as 1.5. So you have to calculate that the possible focal length, that is the focal lengths of possible lenses. So when the lens is converging lens, so we will see two cases when the lens is converging lens. So converging lens is possible in two scenarios, like this and this scenario. So that is the double convex lens or biconvex lens, and second is the concavo convex lens. So in case of concavo convex lens, this must be equal to 20 and this must be equal to 30, as in case of concavo convex lens, the convex surface has steeper than the concave surface, that is the radii of curvature of convex surface will be less, and this is our convex surface. So if we calculate the focal length, then the focal length is equal to, by using lens maker's formula, 1 by f mu minus 1 by r1 minus 1 by r2. Now we apply for these two cases. This is our case 1, this is our case 2. So for case 1, we have 1 by f is equal to 1 by 2 into 1 by 20 plus 1 by 30. It is 1 by 2 into 5 by 60. It is 1 by 24. So focal length is equal to plus 24. So you see that the focal length comes with a positive sign. It means it's a converging. So, and if we see the second figure, then here 1 by f is equal to 1 by 2 and 1 by 20 minus 1 by 30. So here this direction is positive, opposite direction will be negative. So clearly 1 by 2 into 63 minus 2, that is equal to 1 by 120. That is f is equal to plus 120. So if this lens acts as a converging lens, then the possible value of focal length will be plus 24 and plus 120. Now the two cases when the lens acts as a diverging lens. So second B is when the lens will be diverging lens. So for diverging lens, we have two situations. First is this one, and second one is when the lens will be convexo-concave lens. So this is our convexo-concave lens, where this surface is concave surface and it has a less radii of curvature, so it must be 20, and it will have more radii of curvature, that is it must be equal to 30. So again, if you apply the concept, if you apply the formula here, it's a r is equal to 20, r is equal to 30. So you get 1 by f is equal to 1 by 2. For this figure we call it figure third, and we call this as a figure 4. Then for figure third we have 1 by minus 1 by 20 minus 1 by 30. So the value comes is equal to minus 24. F is equal to minus 24. I think these concepts are clear to you. So for figure 4, if you apply this concept, the formula, then 1 by f is equal to 1 by 2. Again r comes with a negative sign, so minus 1 by 20, and this also comes with a negative sign, so minus plus, so 1 by 30. And here if you see it, it comes equal to minus 1 by 120. So f is equal to minus 120. So the possible focal length of possible lenses is equal to plus minus 24 centimeter and plus minus 120 centimeter. So in this way we have learned the lens maker's formula and its application.